right, so thank you everyone for coming to tonight's webinar. So tonight we're going to hear from Colin Lennox, who is one of our founding members and Chief Operating Officer of Settling Space and the Philadelphia chapter of the Mars Society. So tonight Colin is going to talk about his other business. So Colin is also the CEO of Eco Islands, which is a local bioremediation, local to Pennsylvania anyway, bioremediation company that specializes in mine water remediation. And so the system behind that is going to be the core of Colin's talk today. So he's going to be specifically talking about self-organizing wetland bioreactors, which through a miracle of fluid engineering and awareness of biological systems allows for a very passive process to precipitate out heavy metals and other dangerous toxins from mining water, which can be useful both on Earth and in our upcoming ISRU in space. But take it away, Colin.
You see, the thing I love about that is you say it better than I do. And I invented the damn process.
Written it up like 20 times this week.
Yeah,
okay,
well,
so
true. Yeah,
I've got a quick first question,
yeah,
which is the resulting process is precipitation, not sequestration.
It is sequestration, precipitation, and it's going to be the products being solid, liquid, and gas. And salts though, and then you want to dive even deeper into solutes, but that would be slides number 16 through 19 or something like that. So
okay.
Great first question.
So I was checking on the metals in specific. The metals that are oxidized are held biologically, or they're dropped precipitatively, or both. Correct.
Yes, yeah, and in some cases, like manganese oxide or low pH iron oxidation, where you're producing either ranciaite, which is a manganese form of mineral, with manganese oxide, or shortmanite, goethite, or jarosite, which are all low pH iron minerals, or formed under low pH iron conditions through low pH iron oxidizing microbes, generally archaea. So they'll be producing a much higher purity, so to speak, a lot denser minerals in microgranules that kind of look like popcorn as then they grow. From looking at XRD or X-ray diffraction, and but more important, that's how we characterized the actual mineral, and the rest of it was through scanning electron microscopy to actually look to see, like, oh, hey, yeah, looks like popcorn. Hey, that looks like a what would they call that? Not a mycorrhizal, a chitinous passage. And that was or Nathan Pennypacker, who did as an undergrad, had some of the most interesting manganese stuff. But yeah, let me go ahead and do a share screen here, and we'll start this off. And I'd like to coin. Oh, that's the cat. I would like to coin a new term called the. Can you guys see the background there, or did I forget to do the screen share?
Oh.
Okay, 1 second here.
Nope. Yeah, we have you.
Yep.
In the room.
Yeah, the cat just decided to have the most wonderful time to start messing around with me.
The cat is great ASMR during the video, though.
There we go.
Okay. All right. Sweet. Okay. So we'll do a presentation here. Now, this is an adaptation from the 2019 Mars Society presentation that I did. And I'm coining a new term here, and I'm calling it a Sisyphus. Kind of like Sisyphus or Sisyphus, where it's a semi-enclosed or semi-closed ecological life support system, as opposed to an ECCLSS, or an environmental control and life support system. Because an actual ECCLSS is chemical, biological, mechanical, physical, electrical, and it doesn't have any, from what I can tell, and especially the older ones. New ones, I'm sure, could be different, but it lacks that biological component. But even saying biological isn't enough. It's got to be ecological, because once you start bringing in the breadth of natural attenuation and all the microbiology inherent in our 3.5 billion years of evolution, then it becomes that ecological control, and that's where the system then becomes greater than the sum of its parts, because of either products produced or the 1 to 2 exponents of energy saved in the production or cycling of material, whether that be regolith, atmospheric, nutrient, waste cycling. So catalyzing natural attenuation with manufactured wetlands for Earth, Mars, and the Moon. Of course, I'm Colin Lennox, COO of Settling Space and CEO of Eco Islands LLC. And then shout out to Michigan State there, Student Greenhouse Project for the graphics. Thank you, Phil. Yes, we are liberally using those and making sure you get a plug at every opportunity.
No problem.
Yeah,
Thanks.
yeah, totally. Sure. maybe I have to move this out of the way a little bit there. Okay, so what is a wetland? Loosely, this one's easy, guys. Think of a wetland, like close your eyes. What do you see in your mind when you see a wetland? And probably something like what's in the background there, which was that background is a picture from when I went down to South Carolina, and it was one of the most beautiful weddings I've ever seen. I love that picture, and boy, looked like a wetland, so let's go for it. But it holds water. Okay, not a big surprise. There's a lot of water. Produces energetically reduced or oxidized products, solids, solutes, and gases. Phil, that's where you actually slide to, and one of the ones later on. It has a high biofilm mass, organic matter surface area, plants, breaking down material, dead critters, soil particles, organic and biological flock just floating through the water as total suspended solids. And it's, of course, there's an energy source and a nutrient source and a carbon source of one form or another. And the handing off of those different energetic, we'll talk about redox couplets here in a little bit, the handing off of those different materials is then what determines the vibrance and the complexity, and thus the overall products of a wetland, and then more specifically a wetland that works, which is why we're talking bioreactors here. And then ultimately it's also self-organizing, or that natural attenuation, leading to self-selecting unique wetland habitats. So self-selection, whether the proper metabolites are available, will determine what grows. It's as simple as that, you know. And then that self-selection, depending on the biogeochemical properties of the different material, and by and large, chemical, and you know, it's if you go back to periodic table of the elements, a lot of this is really just based off of electron shells. It's that is the synthesis of bioremediation, whether it be direct or indirect bioremediation, and I'll talk about that later. But it's just, you know, it's just shuffling electrons, you know, and oxidizing and then reducing. You're always handing off an electron. And then leading to self-organization then in these unique wetland habitats here, and you can call that a niche, where specific work is being done, and that can be easily predicted if you know what's going into the system. You can monitor it going through, and then you control, and I'll talk about this more a little bit later on, the prime manipulations, or the primary indicators. Then you can make sure that you don't get stuck. Like, you know, you say you're going down a hill and you hit a rock, you know, well, this little bit of information allows you to figure out where that rock is and keep on rolling downhill. And that's where intelligent understanding of the system, almost said intelligent design there. Mm-hmm. Don't want to do that. But the basic ideas of reducing an oxidation that yield more and or less energetically available redox couplets. That's a synthesis of bioremediation right now. That's only the second slide, so I'm going to keep on moving. Okay, so what is biofilm? Mix of microbes and their secreted colloids. When you wake up in the morning and you get that stuff on your teeth, that's biofilm. It's generally stable in mass and population diversity and density. It protects the microbes. Biofilm is kind of like sticky clothing that microbes can talk to each other to and share genetic information and eat other things and be consumed in turn. This is the wild, wild west for microbes, is the biofilm that they're excreting. And colloids, by the way, is like mayonnaise, or kind of like an emulsion of water, polar and non-polar molecules. The main component in natural cycling, you know, if you think about 800 million years ago during the Great Oxidation Event, you know, a lot of that was occurring from natural cycling, self-organization. A new metabolic pathway came along that was much better than what had existed up to that point. And then it spiraled up, and now we've got an oxidizing atmosphere as opposed to a reducing atmosphere. And then that set the stage for everything else to happen down, you know, the last 800 million years. So biogeochemical cycling is another way of saying natural attenuation. Let's see, the big thing is that it hosts complex redox reactions, and I'll go into that more here in a bit. Okay, so what is a bioreactor? It does producible and predictable work. And work, I'm thinking in the classical term here, like you're thinking newtons or ergs or kilowatts or whatever. An easily quantifiable means of knowing something happened over a period of time. So it's in this case, the bioreactor is a biological engine, and it's ruled by the law of conservation of mass and energy. The science that I've chosen is actually pretty darn easy, because water comes in, goes through a box, things happen, water comes out, measure in, measure out, sometimes you measure in the middle. Law of conservation, energy, and mass, it went somewhere. So if it's not there when it's coming out, it's in the box, and if it hasn't become some solid, it off-gassed. Or it's a salt and it just passed straight on through, but you'd be able to measure it for that. Wetlands are notoriously bad at doing salts of any kind. We only need so much salt in our bodies to be able to maintain our osmotic pressure. And same thing with wetlands. It's really not much of a difference. So a lot of times you can measure things like retention time or residency on the amount of salt that moves through a system, because what goes in is going to come out by the vast majority of it, because it is not a useful metabolite. And if anything, in most cases, can be a poison. Think about, that classic microbiology onion experiment where you put a little bit of salt on the side or a saline solution, and you watch the cell wall either explode or desiccate and suck in. So catalyzes reactions producing useful byproducts. Hydrogen sulfide for sulfuric acid. Different forms of minerals, manganese oxide, iron oxides that are capturing rare earth elements, perchlorate, oxygen, carbon dioxide from calcium carbonate degradation, a lot of things, all these biogeochemical cycles, everything that is represented here on Earth. From near as I can tell, we can also replicate on Mars or above using wetlands and I'll get more into this later, as long as the biology is available to reconstitute niches that are lost. And that's the key. And this is where CRISPR-Cas9 coming in is so, this would never work without CRISPR-Cas9. I've got to be the first to admit that. Because if you lose it, if you're up there and you lose it, it's gone. How do you reconstitute something like that? It's not until the technology existed that we could do that. Now we have to catalog everything that is here. That way we can replace it up there. But we're looking at billions of species. But who cares with AI anymore? I don't see this as really something that would stop us anymore. We have everything that we need right now to make this kind of push happen. This moonshot can be a Mars shot because it's not that far anymore. Let's see. So difference between unintentional reactors and intentional. A natural wetland, but a natural wetland destroys itself over time. It fills in. The water has to go the other way around. Well, that's a stream bed now. It's not a wetland. That's two different things. It doesn't allow for the same amount of redox couplets. It doesn't have the greater diversity. The water's moving faster through the river. There's just certain things don't have time to get done before it moves through that area and then eventually down to the oceans. Versus intentional bioreactors or constructed or manufactured wetlands, and this is what we build, which grow biofilm to generate environments and products to sustain human and ecological survival indefinitely. Difference between a constructed wetland, a manufactured wetland, and a natural wetland. Manufactured wetlands can be easily cleaned out and set back to 95% clean, open area. Some environments, that's not a good thing. Maybe you only want 60%. So you only clean it out as much as you actually need to, versus a constructed wetland, which has to be, in most cases, totally ripped back up in 10, 15, 20 years when it's filled in, and then reconstructed for close to the same cost as initially required, and it requires heavy construction equipment to do it, versus a manufactured wetland where now we're building auto siphons into it. These things will clean themselves. That's been a major step for us just recently. Okay, examples of biofilm reactors or bioreactors. Natural wetlands, methane digesters, reclamation ponds, fish tanks, greenhouses, wastewater treatment plants, wine and beer vats, Carboys, like the one sitting right behind Phil. People, plants, boxes, turtles, and my dog, Ripper. Or my cat, Megan. Because we're all just bags of mostly water. Like, I don't know if any Trekkie nerds out there, or Trekkie or Trekker, I can never remember which one's which. But the crystalline entity calling us bags of mostly water, that was one of my favorite episodes. It ain't a lie. You know, we're what, 90-something% water anyway, somewhere in around there. And I'd like to make the argument that we're just walking bioreactors. We have purpose, we get work done. Why not? It's a loose definition. Okay, so the indicators and adaptations, let's see, what's that? Auto or manual. So oxidation reduction. This is how, okay, if you're actually out in the field and you're doing wetland remediation for, say, mine drainage or wastewater treatment, if you know a whole lot, if you can get these 5 basics, and the equipment is really pretty easy. You got your ORP probe or your oxidation reduction. These things cost like $50. I mean, and all it's doing is it's measuring, it's sending it, it's an electrical probe, and it is determining what the state is, the ORP state is, and it'll tell you in millivolts, and it'll either be +0 to, I don't know, it could go up to 1,000 if you're talking like battery style systems. Biologically, you're generally not going to get much over a +450, and then it'll be about a -450 or so for methane reduction. Also a biological system, and that's about the bottom end of the available, and anything lower than that, and the redox couplets aren't providing enough energy to keep that critter alive. It's just, there's not enough, as James would say, there's not enough juice for the squeeze, so to speak. Versus aerobic oxidation, when you think about all the energy that you get out of methane, where you've got a +450 and a -450, and if you don't actually burn it, but you're using a biochemical cell, that's 9 volts, or excuse me, 0.9 volts. -450 millivolts, +450 millivolts, it's 0.9. And that's something that I can back up here and have seen through personal experimentation as well. And that also then determines the energetic efficiency of what you get from burning methane. They're very close, and so if you think of all of life like a battery that needs recharge, more like a fuel cell, but it totally comes into play. Okay, coming back down off the higher clouds there, flow. Easy one to know, get a bucket and a stopwatch. If you need to slow things down, or conversely, speed things up and get the water running faster through a system. One of the things that is not, it's accepted but not generally done, is build a system that's actually smaller to run faster. Usually in mine drainage systems, it's built as big as you possibly have available, biggest darn pond, and then just don't worry about it. I'll be retired in 20 years. We'll let somebody else deal with it. Well, I think that's kind of bullshit. But that's the way it's done. And in some cases, you can get away or get around that by actually speeding up the flow, get more oxygen into the system. If oxygen is your limiting metabolite, so to speak, in this case, a terminal electron acceptor, get more oxygen into the system, run it faster. You have to have turnovers. And these are design considerations that are usually, they're understood, but they're harder to put into place in a constructed wetland where you have to build it with big machines versus a manufactured wetland where we can build it into the facility as we're constructing them, or as we're manufacturing them, and then send them out on the site, set them up, and you have much finer quality control, and you've got a lot more capability to build a better structure as opposed to a bunch of Jersey barriers with a liner over top of it and hoping that's going to do the job, because a lot of times it doesn't. pH, litmus strips. Pretty much everybody knows pH. I'll move on. Temp, obvious one. Colder, warmer, deals with your metabolism. Obviously, very cold temperatures below freezing are teeming with life. So it depends on your solute concentrations. And then, say to methane digesters, you've got your mesophiles and your thermophiles. And, staying around like 98 degrees would be like perfect, versus the thermophiles. Maybe you want to jump up to a 140. I don't know how you'd say it, hydrophiles, or those acidophiles. There we go. Things like going back to pH, low pH iron oxidation. They're specifically modulating the pH within their environments and they're doing so based off of their metabolic rate, because the hydrogen ions that are the acid are produced as the byproduct of ferrous iron oxidation. So if it's getting a little too hot for them, they slow down. This is where biofilm is very useful, where they are capable of modulating their own environments so long as the environment is generally stable, and that they are capable of, or they've got plenty to work with. You know, they still have enough ferrous iron, got enough O2, got enough carbon dioxide. And then down at the bottom, then electroconductivity. This another parameter of osmotic pressure. They also, I've seen salinity and total suspended or total dissolved solids used. But after going back in, it looks like electroconductivity is what's really should be used the most. And is also, it's easy to directly relate EC to redox as well. So it's a cleaner set of measurements that are you can take out some of the factors and the guesswork, or not guesswork, but it cleans up the system.